Usually when we talk about computer code or software engineering, there is this fundamental expectation of absolute uncompromising precision.
Right, yeah. Like you expect it to just work.
Exactly. You write a specific line of code, and the machine executes it exactly as written. I
Hmm.
mean, it feels a lot like looking at a medical X-ray.
Oh, that's an interesting way to put it.
Yeah, because if you break your arm, the X-ray shows that stark, jagged white line against the black background. The doctor just points at it and says, there's the problem, plain as day.
It is a very comforting way to view technology for sure. We naturally gravitate toward systems that are binary, predictable and visually clean.
Right, black and white.
Exactly.
Hmm.
If a classical computer throws an error, there is always a tangible, traceable logic path that leads you right back to the bug.
But then you step out of that classical world and into the realm of quantum computing and molecular simulation, and suddenly that crisp X-ray machine is completely shattered.
Oh, absolutely. It's totally gone.
The physical hardware is fuzzy, the underlying math is impossibly tangled, and the computational landscape we are trying to navigate is, honestly, it's incredibly murky.
It really is the ultimate diagnostic blind spot, especially when you get down to the nanoscale where these quantum devices actually operate.
Because it's just so tiny.
Right. The physical reality is profoundly messy. We are dealing with individual atoms and electrons, and at that scale, I mean, nothing is pristine.
Welcome to today's deep dive into the source material. We are going to explore a massive, thrilling paradigm shift for you today.
And we've got some incredible sources to back this up.
We really do. We're looking at a stack of brand new research. We've got an Oxford study on quantum hardware, a fresh March 2026 paper on physics-informed program synthesis, and some really cutting-edge work on neural networks.
And it all points to one undeniable conclusion.
Which is that we are moving away from artificial intelligence being just a black box that spits out statistical guesses.
Right. Instead, scientists are fundamentally teaching AI the immutable laws of physics.
And by teaching AI those foundational rules, it is suddenly able to solve two of the hardest, most stubborn problems in modern science simultaneously.
Which is just wild to think about. Accurately simulating nature, like complex chemical reactions, and actually building functional quantum computers.
The hook here, and what makes this so crazy for you listening, is that the AI isn't just following our instructions to solve these problems. It is actively writing its own physical shortcuts.
Yeah, it's bypassing us entirely in some ways.
So let's unpack how it's doing this, starting with the hardware. Because before we can even dream of using a quantum computer to simulate complex chemistry, we have to acknowledge a dirty little secret in the physics community.
The physical chips themselves are inherently flawed.
Right, and this is what researchers in the Oxford study refer to as the reality gap.
The reality gap. Yeah, whenever you design a quantum device, like say a quantum dot array, you start with a perfect blueprint in a computer simulation.
And in theory, it behaves beautifully, right?
Oh, in theory, it's flawless. But when you actually manufacture that device and put it on a laboratory bench, it behaves entirely differently.
Because of the nanoscale imperfections.
Exactly. The physical device is riddled with them. Stray atoms, slight material variances, tiny deformities, things you literally can't avoid.
And the most frustrating part is that scientists can't just crack open the quantum chip, throw it under a microscope, and look for the flaws.
No, because the very act of measuring or looking at a delicate quantum state collapses it.
Which leaves engineers essentially flying blind.
Totally blind. You have a device that isn't working the way the blueprint says it should, and you are physically forbidden by the laws of quantum mechanics from directly looking inside to see why.
It sounds maddening. So the Oxford team took a completely different approach. They used physics-informed machine learning to infer all of that internal microscopic disorder indirectly.
Yes, simply by measuring the flow of electrons through the device at various voltage settings.
I was reading their paper, and there's an analogy in there that completely changed how I see this. I want to share it with you, the listener, because it makes this invisible process so accessible.
It's a really brilliant analogy.
The researchers compared their method to playing crazy golf in a pitch-black tunnel.
Right.
You're standing at the entrance with a golf club, and you know the tunnel is full of invisible ramps, bumps, and curves, but you can't see any of them.
You're just hitting into the void.
Exactly. So what do? You start hitting the ball into the darkness hundreds of times. You place sensors at the exit of the tunnel to measure exactly how fast the ball comes out and at what angle.
And by feeding all that exit data into an AI, The model eventually reverse engineers the darkness.
Right. It draws a perfect map of every invisible obstacle inside the tunnel.
It perfectly captures the mechanism at play, because in the actual quantum device, the golf swing is the voltage being applied to the gates.
And the golf ball is the electron.
Exactly, the electron flowing through the quantum dots. The AI looks at how the current changes when the voltage shifts.
But the real breakthrough here isn't just that the AI draws a rough map of the disorder, is it?
No, not at all. Because the deep learning model is strictly bound by the actual physical equations of electron transport, it mathematically quantifies the disorder.
Meaning it knows exactly how steep that invisible ramp in the tunnel is down to the millimeter.
Well, far smaller than a millimeter, but yes.
Right.
And once the AI quantifies the exact nature of the microscopic flaws, engineers can calculate the precise voltage settings needed to compensate for them.
So they use the AI to effectively neutralize the hardware's unique physical defects without ever having to look at them.
Exactly. It's an elegant solution to an impossible problem.
That is just brilliant. But it naturally brings up a massive secondary issue. If every single quantum chip rolling off the assembly line is uniquely flawed,
Which they are.
right? If every chip is its own distinct, bumpy, crazy golf course, how on earth do we write reliable software for it?
That is the million-dollar question.
Because in classical computer science, the absolute holy grail is universal code. You write an application once, and it runs on my laptop, your phone, and a server in Tokyo.
Write once, run anywhere.
Exactly. Are we saying the future of quantum computing completely abandons that universality for hyper-customized algorithms that only work on one specific faulty chip?
We are abandoning universality, yes. At least for the foreseeable future.
Wow.
Quantum hardware is currently so fragile, and that reality gap is so wide, that trying to force universal code onto a uniquely flawed chip is a massive liability.
It just breaks.
It simply produces too many errors. To get these machines to do anything useful, we have to let AI write bespoke, highly specialized software tailored to the exact error profile of an individual machine.
Which brings us to the fascinating study on synthesizing hardware-optimal quantum algorithms using POMDPs.
Yes.
And just to define that alphabet soup, it stands for Partially Observable Markov Decision Processes.
The partially observable aspect is the critical link here.
How so?
Well, just like the golfer in the dark tunnel who can only see the ball at the exit, a quantum computer can't observe its own quantum state continuously without destroying the calculation.
Right, the measurement problem we talked about earlier.
Exactly. A POMDP model accounts for this by treating the process of writing an algorithm like a strategic game.
A game?
Yeah. The AI agent takes actions, in this case, placing specific quantum logic gates into a sequence based only on the clues it has gathered from past observations.
So it's guessing based on context.
Right. And its sole objective is to maximize a specific payoff.
And the payoff is the final accuracy of the algorithm. Now, the tasks they were trying to synthesize algorithms for are foundational to making quantum computers actually work.
Very foundational. We're talking about basic operations.
They looked at quantum error correction, specifically something called the parity bit flip problem. A bit flip is essentially when a qubit accidentally flips from a 0 to a 1 due to environmental noise.
Yeah, it's like a corrupted letter in a text message. Just a random glitch.
They also looked at state preparation, like generating GHZ states, where multiple qubits are perfectly entangled to act as a single unified system.
And those entangled states are notoriously delicate.
I can imagine.
If a single qubit in the hardware is slightly more susceptible to noise, which the AI knows because it has the specific error profile of that exact chip, the entanglement shatters.
So the POMDP model plays its game, constantly asking itself, given the unique flaws of this specific hardware, what sequence of gates gives me the highest probability of protecting this entangled state?
And through playing that game, it mathematically guarantees the absolute best sequence for that exact machine.
The results they got when they tested this on real physical IBM hardware are staggering. I mean, let's look at the error correction first.
The numbers speak for themselves.
The AI synthesized a bespoke algorithm named CX plus H1. They deployed this onto the noisy qubits of a specific IBM machine called the Cambridge hardware.
Okay, so keep in mind, using traditional one-size-fits-all methods, the error correction accuracy on that machine was sitting at 61.13%.
The AI's bespoke algorithm spiked that accuracy to 95.2%.
To put that in perspective, 61% accuracy in quantum error correction is effectively useless.
Really useless.
Yeah. The noise will eventually cascade and destroy your calculation. 95.2% pushes the hardware into the realm of actual viability.
That's a massive leap.
It is, but the contrast becomes even sharper when you look at how the AI performed against industry-standard software tools.
You're talking about the IBM QuizKit transpiler.
Exactly.
For context for you listening, a transpiler is a piece of software whose entire job is to take generic quantum code and adapt it to run on specific hardware.
And standard transpilers rely on pre-programmed heuristic rules. They don't truly understand the messy physics of the specific chip the way our crazy golf AI does. When researchers used the standard transpiler to prepare a G8Z state on the IBM Manhattan hardware, it failed spectacularly, yielding an accuracy of just 6.1%.
6.1% isn't even an attempt. It's just random noise.
It is complete static.
But when they handed that exact same task on that exact same Manhattan hardware over to the POMDP method,
The AI synthesized a unique sequence of gates that dodged the hardware's specific flaws and achieved a 98.1% accuracy.
it is almost difficult to wrap your head around. It's like finding out the transmission in your car is completely shattered.
Yeah,
But instead of taking it to a mechanic to fix the physical gears, an AI just calculates a hyper-specific, totally bizarre way to feather the gas pedal and shift the clutch so that the car drives perfectly anyway.
I love that analogy. It is neutralizing physical flaws through pure software optimization.
That is the power of writing bespoke algorithms. We stop fighting the hardware's unique physics and start leveraging them. Okay, so we've seen how AI maps invisible flaws, and we've seen how it writes physical shortcuts to run that messy hardware.
Right.
Now let's pivot and look at how AI is finding physical shortcuts in the actual math of the universe.
This is where it gets really mind-bending.
It really does. This brings us to the March 2026 paper on physics-informed program synthesis, or PIPS. We are transitioning here from optimizing the machine itself to optimizing the scientific calculations we want to run on the machine.
And the PIPS research tackles one of the most resource-intensive bottlenecks in all of computational chemistry.
Which is?
Well, when scientists want to simulate how a molecule behaves, they use classical methods like Hartree-Fock or density functional theory. But these methods rely on something called self-consistent field cycles, or SCF cycles.
Okay, let me stop you there. Why do they need a cycle? Why can't they just calculate it once and be done?
Because electrons in a molecule interact with each other. They repel each other, right?
Negative charges repel.
Exactly. If you want to calculate the energy state of electron A, you need to know where electron B is.
Okay, that makes sense.
But the moment you calculate electron B's position, its repulsion shifts the state of electron A.
Oh, I see.
It is a massive multi-body problem. So the computer makes a best guess for all the electrons simultaneously. It calculates the forces, realizes the guess is slightly wrong, adjusts all the positions, and runs the entire complex calculation again.
Just going around and around.
Exactly. It iterates through these massive loops until the answers finally stop changing, until the field is quote-unquote self-consistent.
And I imagine that takes an enormous amount of computing power.
An unbelievable amount.
Let me try to visualize this. It sounds like trying to solve a brutal, expert-level Sudoku puzzle.
Okay, yeah.
The SCF cycles are like doing it the traditional way. You pencil a number into a square, then you check the row, then you check the column.
Right.
You realize it conflicts with a number in the corner. So you erase it, adjust your guesses, and check the whole board again. You do this over and over until the grid finally balances.
That's the perfect way to describe the iterations.
But what this new PIPS AI did, it essentially found a hidden mathematical backdoor that allows you to look at the blank Sudoku grid, and instead of guessing and checking, it just hands you the completed puzzle in a single synchronized move.
That captures the magnitude of the shortcut perfectly. The PIPS system completely bypasses the iterative loops.
Skips them entirely.
It discovered entirely new algorithmic methods that achieve the exact same molecular orbital coefficients without performing a single SCF iteration.
Wow.
It replaces the entire trial and error process with one massive synchronized mathematical step known as matrix diagonalization.
But wait, how does an AI even do that? I thought machine learning models were essentially pattern matchers.
Usually they are.
You show an AI 10,000 pictures of a bicycle, and eventually it can guess what a bicycle looks like. If it's just guessing at the molecular energy based on training data, how can we trust it?
That is the crucial distinction here. Typical AI is a black box that outputs a statistical probability. It gives you a number.
Right, a best guess.
PIPS does not output a number. It uses a technique called symbolic regression.
Symbolic regression.
Yes. Instead of a statistical guess, the AI outputs an actual, discrete algebraic equation.
Oh, wow.
It writes a tangible mathematical program that operates directly on the atomic orbitals.
So it's literally doing the math.
Yes. Because it generates real math rather than black box approximations, it fundamentally maintains the underlying quantum physics of the molecule. But by skipping the SCF loops, it executes with the blazing speed of a traditional, simplified force field model.
The numbers in the paper back that up in a big way. The energy accuracy they achieved was roughly 0.1 kilocalories per mole per atom, which is incredibly precise.
Unprecedentedly precise for a shortcut like this.
But the detail that really stopped me in my tracks was the training data. The researchers only trained this AI on a tiny handful of extremely simple molecules.
Just methane and ethane.
Right.
It was a total of 36 data points.
36. For a machine learning model, 36 data points is practically nothing.
It's absurdly small.
Right. But incredibly, the mathematical equation the AI wrote didn't just apply to methane and ethane.
Oh, it didn't.
They took that exact same AI-generated equation and tested it on much larger, more complex hydrocarbons that the system had never seen before.
Things like propane and butane.
And the shortcut works flawlessly.
Which definitively proves that the AI did not just memorize the answers for the training data.
Because it couldn't have.
Exactly. By using physics-informed symbolic regression, the AI actually learned the fundamental physical mechanics of how atoms interact. It discovered a universal mathematical shortcut that holds true even as the molecular systems scale up in complexity.
So PIPS gives us this incredible mathematical shortcut for running chemistry simulations on classical computers.
It does.
But what if we want to run these chemistry simulations directly on the bespoke, hyper-customized quantum chips we built earlier?
Right. How do we combine the two breakthroughs?
Exactly. The AI needs to translate this elegant math into physical quantum circuits. Which brings us to our final source, the ArcSiv paper on physics-informed neural networks, or PINs.
This is the bridge that connects the theoretical math to the physical quantum hardware.
I see.
The researchers in this study were focused on optimizing quantum circuits for real molecular systems. Specifically, they were simulating hydrogen gas, which functions as a 2-qubit system.
And lithium hydride.
Yes, lithium hydride, which operates as a 4-qubit system using the STO3G basis. Their goal was to perform optimal counterdiabatic quantum computation.
Okay, counterdiabatic. Let's translate that for you listening. In simple terms, it's a technique used to speed up a quantum simulation rapidly, but without losing control of the stable quantum state.
Right.
It's like trying to run at a full sprint while carrying a cup of hot coffee filled to the brim.
Yeah.
You want to go as fast as possible without spilling the delicate quantum information.
That's a great way to picture it. But finding the exact sequence of quantum operations to achieve that high-speed, stable state is incredibly difficult.
I bet.
So they used a neural network to hunt for the optimal circuit. However, to ensure the AI didn't suggest something physically impossible, they strictly constrained its training.
Constrained it how?
They forced the network to obey two fundamental rules of reality: the hermeticity condition and the principle of least action.
But wait, why force the neural network to obey these rules at all? Left to its own devices? Would the AI actually start hallucinating quantum states that violate the laws of physics?
Yes, absolutely.
Because we've all seen large language models confidently invent historical events that never happened. Does a scientific AI do the same thing with the fabric of reality?
It absolutely can. If you let an unconstrained neural network optimize a complex system, it will relentlessly hunt for the most mathematically efficient shortcut, regardless of whether that shortcut can actually exist in the physical universe.
So it might just break the laws of physics on paper to get the answer?
Exactly. It might output a circuit design that relies on imaginary energy states.
Oh, wow.
The hermeticity condition mathematically guarantees that the AI's output will always result in real, observable physical values.
And the principle of least action, what does that do?
That is one of the most beautiful rules in physics. It dictates that nature always takes the most efficient path.
Like a river carving the path of least resistance down a mountain.
Precisely. By hard-coding this principle into the loss function of the neural network, the AI is mathematically forced to not just find a valid circuit, but to find the single most elegant, physically efficient path to simulate the molecule.
And the output that this highly constrained neural network provides is Incredibly practical.
Very practical.
It outputs the circuit design as a clean, linear combination of Pauli operators.
And poly operators are essentially the machine code, the fundamental vocabulary of quantum computing.
So it's speaking the native language.
Yes. Because the physics-informed AI speaks this language natively, its output can be programmed directly and seamlessly into the very quantum computers we just finished optimizing with our POMDP models.
The entire process becomes a closed, self-reinforcing loop.
Exactly.
It is breathtaking to step back and look at the whole picture. We started in the dark, with the murky, imperfect reality of quantum hardware, where an AI acts like a golfer mapping out invisible microscopic flaws just to close the reality gap.
From there, we watched AI abandon the classical dream of universal code,
Right.
opting instead to synthesize bespoke, hyper-customized quantum algorithms that mathematically neutralize the physical errors of specific chips,
And then we saw AI dive into the exhaustive, iterative math of molecular chemistry.
discovering a hidden backdoor that replaces decades of tedious SCF loops with a single mathematical step.
And finally, we saw neural networks strictly constrained by the laws of thermodynamics and hermeticity, translating those simulations into flawless quantum circuits without hallucinating impossible realities.
We are looking at an era where AI is no longer just a tool for processing large data sets.
It has become an active, independent partner in uncovering the mechanical secrets of the universe.
It is a profound shift in how we do science. And, it leaves us with a fascinating, almost unsettling question to consider.
Oh, let's hear it.
If a physics-informed AI can independently discover a one-step shortcut to a quantum chemistry problem that brilliant human scientists have been solving with tedious, iterative loops for decades, what other foundational scientific laws or mathematical procedures are we currently doing the quote-unquote long way, simply because the human brain isn't wired to see the shortcut?
That is a question that will definitely keep me up tonight.
Yeah.
Are we just taking the long way around simply because we can't see the back door?
It makes you wonder.
It really does. Thank you for taking this deep dive into the source material with us today. Keep questioning the path you're on, and we'll catch you next time.